Hi everyone, how's it going? And welcome to the adaptation to exercise of the nervous system section of this chapter. Let's dive into it. So one of the first concepts that we're going to cover is what's called like a neural drive. And so the way you can think of it is as like a volume or a dial for the amount of output that the brain will send to the body. Okay, so this is coming from the central nervous system, so your brain stem in particular, because it's not something conscious that we typically control. And so from this, again, you can think if there's more neural drive, there's more volume turned up to your nervous system, so we're more likely to recruit more motor units. And we can carry more tension through our body. The other way to think about neural drive is if you're considering the way we stand or the way we sit, we don't really think of it. There's just this kind of like tone or, again, this neural drive that's put out into our body to help kind of maintain just this constant, again, volume, if you will, of nervous signals or nervous outputs, okay? And so one of the things that we do while we exercise, and the way we can kind of measure this, is the amount of motor unit recruitment and the rate coding of our active motor units within a muscle. And so I think a good example of rate coding is something that we kind of held off from last chapter to discuss, to chat about now, is this idea that the way our muscles contract or summate in their contractions really varies on the frequency of your action potential. So for example, we have an action potential in a neuron go here, the muscle will contract and then relax. And then, again, if we're going at a rate of about 5 hertz, so that's a frequency, you can say 1 every 5 seconds is roughly about 5 hertz. Versus something at a higher frequency, so again, evenly spaced out every so 1/10 of that time, we have a higher frequency of action potentials causing a continuous and increasing contraction of our muscle. And then more so at 20 and that 40, we have what potentially you could call as tetanus. So just a steady state contraction, maximally contracting. And that comes from increasing the number of action potentials. So again, that occurs here where we have our neural drive increasing. So as I mentioned, it comes from the CNS, which then gets sent out to our peripheral nervous system, or our PNS, and it increases the contractile response. So the capacity for our muscles to contract, it increases that for any submaximal amount. Increases the maximal total amount of neural drive, so it increases our total amount of strength that we can handle as our neural drive increases maximally, and it increases how many motor units are firing, and thus because of that we see an increased force and rate or speed at which our peak force is generated. So again, turn up the volume, you turn up the capacity of our muscles to contract in all ways. If we are to look now specifically at strength training, okay, so we'll kind of shift gears. So we're looking at a model here of strength training. The goal typically being hypertrophy, so increasing muscle size in order to increase our strength, or force production is another way to think of that. And so we see over our timeline here, 0, 8, 16, 24, 32 weeks. This is in weeks. So right here would be about 1 month into regularly strength training. Typically, most strength training programs are about 3 times a week for a half hour to an hour. Depending on the study that you're looking at, usually it's up to an hour. And so from here, we can see that at month 4, even though we have a demonstrated increase in strength, we can see that that actually comes primarily and almost exclusively in the first month of your training from your neural adaptations. So for example, you are doing a leg press, you notice that you're going up quite a bit of weight over the first 4 weeks, which generally happens. that is primarily from your neural drive, so your neural capacity to increase connections of motor units, connection or increasing, yeah, so with that increases the amount of muscle fibers that are fired. But again, and through that neural recruitment of motor units is where that strength comes. So you don't actually start seeing any, I would argue, significant changes in hypertrophy of anything notable until about 8 weeks. And you really aren't, when you're going to do your strength training program, increasing your the hypertrophy of your muscles more than your neural recruitment until almost 16 weeks. So if you think about that, that's 4 months. So after 4 months of strength training, essentially you're purely developing and training your neurological system. And if you think about how our nervous system controls and recruits muscle, this should kind of make sense. So once we get to a point somewhere here after 8 weeks where we're plateauing with our neural drive and influence over our hypertrophy or our muscle motor unit recruitments and our muscle fiber recruitments, that's when we purely start or I'd say we largely start creating enough stimuli or breaking down our muscle enough to cause some repair and rebuilding or hyper building on top of whatever the stimuli was to really develop this hypertrophic state. And then from this point on, it shows like there's not much progress or whatever. But again, as time goes on, this, depending on what your training program is, can kind of continue on upward from there. Okay. So this is, again, just when people are starting out. And I should note, too, at this point in time that as we detrain, we'll notice a very similar pattern where the neural recruitment of our motor units decrease quite quickly, and the hypertrophy doesn't quite decrease as quickly. It lags behind quite a bit, but when we go to start up a program again after a bit of a break, the increases in strength that we see at that point in time, or force production or force capacity, is largely our nervous system recruiting muscle again. And so here we'll look at a slightly different set of how our nervous system will recruit muscle or be trained. And what we'll be doing is looking at skilled rowers versus unskilled rowers. So what this kind of looks like is the way in which people's bodies will recruit different muscle groups. Because again, a lot of this is coming from our central nervous system, how we trained those motor programs, if you will, to recruit different muscles as we perform a skill, right? So it's the coordination of our muscles to complete a motor skill. So when we're looking at that skill adaptation, again, that's something we learn and have in our brains, our central nervous system. We notice that if we were to take just purely a strength or a power trained individual, we might see a similar initial recruitment pattern as someone who's highly skilled. But because training is very specific, or this idea of specificity of training occurs, our brains will recruit certain motor units which are more purely strength-based if we're a strength-based person. So for example, we have a power lifter, great force production, but it's limited to type 2 muscle fiber because those are the motor units being recruited during that training. So again, in the first, let's say, 2 minutes of exercise, a skilled rower and a strength-trained individual might both excel and demonstrate a very high level of, say, quadricep recruitment and power and force production. But because the purely strength-based individual isn't necessarily specifically trained for rowing, so the motor patterning isn't there, neither is the endurance. So for longer term activity, they essentially after a certain time will slow and their strength and power decreases and diminishes so that they can no longer continue on with the skill. Now, rowing is a pretty full body exercise, to say the least. So when you're performing that skill, what we'll find endurance trained individuals in particular, a very skill and specifically trained in rowing individual, is they might have a very similar start to our power-based individuals, but what they'll be able to do is change their recruitment patterns of muscles. So we'll see if we just follow the quadriceps, they're very quadricep dominant for the first couple of minutes, but then almost very little. But what does pick up is the calf and the back to pick up that slack. So it kind of trades off the percentage of recruitment there. Then very similar, the quadriceps come back for some time, still the quads, but then we see a little peak up here in the brachioradialis, which is in the forearm. And so again, the gist of it is we see a pretty continual summation of all these different recruitment muscle groups as far as the total force they're able to produce, the total amount of work they're able to do, but it's distributed or shared in an organized recruitment pattern fashion across the whole body. Okay, and so that's one of the big differences is in order to sustain a certain level of output, our nervous or neural adaptation will change the recruitment patterns throughout an activity to be able to share the load between muscle groups. And the reason for this is to maintain a submaximal effort of most all muscle groups, so you don't need to recruit type 2 muscle fiber, because again, you're sharing load across the body and giving some muscle groups breaks while others are working. Okay. So again, that was in an endurance and specified or skilled or highly trained individuals. We'll see this kind of recruitment pattern. All right, continuing on with endurance-based adaptations, we see this kind of actual imaging of synapses. Okay, so presynaptic acetylcholine and postsynaptic acetylcholine receptors. Okay, and of course these are at the in our neuromuscular junctions, which is between the motor neuron and our skeletal muscle. And really, aside from just having some very cool imaging here, this actually highlights a few things, and primarily the fact that, or just a reminder that acetylcholine, being the neurotransmitter that is transmitted across the neuromuscular junction, what we'll find is there's more vesicles, so there's a larger capacity in our motor neurons to transmit some of this acetylcholine. But there's also a greater number of receptors on the motor end plate, so on the other side of the synaptic cleft between our neuron and our skeletal muscle. So, and so the point with this being is, like, as we adapt and get trained, our nervous system what happens is it becomes more responsive to less stimuli. So, for example, a smaller amount of acetylcholine will cause potentially a larger response on the other end. So we become more efficient in how our nervous system works at the neuromuscular junction. But similarly, on the top end, so maximum contraction, what we're able to do is fully unleash all of our acetylcholine, and we have way more receptors. So the idea is it causes a much larger response at the motor end plate, so on our skeletal muscle. And so we'll also increase the amount of motor units firing, so create more force. Okay. If we were to look just briefly at our motor cortex and how it changes, I think there's, aside from just this image being interesting, there's a couple of other interesting points to note. But they've done EEG, so electroencephalographs. You might have seen those in movies. They're like the caps you put on with all the wires coming out of them. But Yeah, so they've done EEG, two E's, one G, studies of different types of exercise, and they note that depending on whether you're trying to do high power, high force, so high power would be a large amount of force in a quick amount of time, or a short amount of time. High force is just generally maximally trying to produce peak force, like a 1 rep max, let's say. And then high volume is like more of an endurance-based type activity. We notice that different parts of the brains become more active. Okay, the control is anything green. So when you're reading or looking at images like this, green just means like nothing, and we can tell because the control is all green. And so what they do with these is on top of just a baseline, so they kind of like zero out the scale, so to speak, at this control activity level, and anything above that is what gets highlighted. So again, when we see red, that's highly active, blue is some activity, and what we'll notice, it's just the different regions. So for example, with high power activity, it's a lot of sensory and motor, so around the middle part of the cortex. With high force production, we see some prefrontal cortex as well as some sensory motor, and then ends up a lot of occipital, so that's our visual center, which is interesting. And then high volume, again, not tons, but towards the end, we see some prefrontal and sensory motor centers getting activated. But yeah, one of the key parts that I wanted to chat about here and with this part is with training different parts of our central nervous system, in particular our motor cortex and sensory motor centers. So that's kind of like right in the middle top part of your brain by your central sulci, if you recall where that was. Those areas get more active. So the idea is over training, and this particular study was just like a finger motor skill. They have lots of different protocols you can use, but usually it's just like finger tapping in a pattern or reaction time stuff. But we can see over the span of 8 weeks of training that this area right here in the trained individuals for this specific task, we can see a greater amount of activation. And because of that, what ends up happening is we get more neurons for that particular area getting active when we perform this skill. Now, interestingly, you can note that, and these slides were the untrained individuals, although you see some improvement because they've done the task before in this study, it's not nearly as much increase in activation, both in size and intensity as the trained session. Okay, the interesting part about our central nervous system and motor training is visualization oftentimes increases these centers as well. So purely just by thinking of the exercise, thinking about recruiting muscles, and thinking about a motor skill can help develop these areas. So when they talk about visualizing motor skill, it truly does help, because that central nervous system area then, when you're actually performing the skill, can help recruit actual muscle when performing the skill. And that can, believe that's been shown for recruitment patterns as well, thinking about the right organization of that. Okay, so to kind of sum it all up in hopefully a bit more of a practical sense than going through it a bit piecemeal, so at the end of the day, the idea of specificity is very key, especially within nervous system. Again, the type of training you do dictates what sort of motor units are recruited, how much of them, as well as the recruitment pattern of those motor units when we're doing a specific skill, okay? So the order and the magnitude of these patterns get trained from our nervous system, both centrally and peripherally. And again, we see that trade-off between strength and endurance athletes, where endurance athletes tend to share the load in their motor recruitment patterns and therefore become more fatigue resistant with their biomechanics, whereas strength trained individuals typically not. They have primarily type 2 muscle motor unit recruitment, just generally because that's what they've trained, and therefore they can't share the load at lower intensities. And again, probably one of the more common and important points to note is that most strength training, both in its positive adaptation and detraining, are largely due to neuronal training. Again, hypertrophy effects don't happen till much later. Okay, and that concludes the exercise adaptations of the nervous system. Cheers.